Right now, you are listening to this deep dive. Maybe you're out on a walk or commuting, or maybe you have another tab open on your screen right now, and you're typing a prompt into an AI model.
Right, asking it to summarize a PDF or write code or whatever.
Exactly. You hit enter, and you get this fully coherent, complex answer in, like, 2 seconds. It feels completely frictionless. I mean, it basically feels like magic.
It does, but, if you could put on a pair of X-ray glasses right now and look past your screen, past your Wi-Fi router, and look at the actual physical infrastructure powering that single keystroke.
You wouldn't
The-
see a pristine, weightless cloud.
No, not at all. You would see a fragile mid-20th century power grid that is absolutely screaming under the weight of a 21st century brain.
Screaming. That is such a vivid way to put it, but it's true. And that collision is exactly the mission of today's deep dive. We are going to explore how the insatiable, frankly terrifying energy appetite of artificial intelligence is forcing a radical, ground-up redesign of our entire global power architecture.
Yeah, we're talking about a convergence that sounds, it sounds like science fiction when you first read the papers.
It really does.
Yeah.
We are looking at nuclear physics merging directly with distributed computing. Specifically, we're diving into what the industry is calling SMR clusters and how they are orchestrating the next intelligence phase. Okay, let's unpack this. We have a massive stack of sources to guide us today,
A
right?
huge stack.
You've got legal briefs from Shoemaker, Loop, and Kendrick breaking down the brutal realities of AI data center power integration. We have deeply technical research papers on decentralized grid logic and this wild concept called the radial brain.
Which is fascinating. We'll get to that.
Oh, we definitely will. Plus, we are balancing the technological hype with the highly critical perspective of the World Nuclear Industry Status Report. And finally, we're going to look at an actual regulatory filing submitted to the Nuclear Regulatory Commission by a company called Oklo.
Right, which details exactly how human beings will, or I guess more accurately, won't operate these new grids.
Yeah, the won't part is wild. But to truly grasp what is happening, you have to look at both sides of the coin.
Exactly, because we are simultaneously redesigning the physical hardware of power-shrinking nuclear reactors down to these factory-built modules, and we are redesigning the digital software that controls them. We're evolving from centralized control rooms into decentralized biomimetic neural networks.
So let's start with the physics of the demand, because when people say AI is hungry, they usually think about, their laptop getting a bit warm in their lap.
Right, and that really doesn't capture the thermodynamics of what is happening at the hyperscaler level. I mean, the transition to generative AI requires tens of thousands of specialized GPUs running concurrently.
Graphics processing units.
Yeah, and every time a billion parameter model processes a token, you have millions of microscopic transistors flipping state. That generates heat. And to prevent the silicon from literally melting, you need massive cooling systems. Both the computation and the cooling require immense continuous electrical current.
Let me contextualize the data from the sources for you, because the numbers here are staggering. We are moving away from the standard data center model you might be picturing, a warehouse full of server racks.
Those are practically relics now.
Right. We're now talking about full-blown AI campuses.
Yeah.
And these facilities are increasingly demanding anywhere from 100 megawatts to over 500 megawatts of continuous power.
To put a 500 megawatt load into perspective, you are no longer talking about powering a building. You are talking about the continuous electricity consumption of a major metropolitan district.
Or like a massive industrial aluminum smelting plant.
Exactly. It's industrial scale.
And the projections from the U.S. Department of Energy and Grid Strategies show U.S. electricity demand surging by 15.8% by 2029. That's an additional 128 gigawatts of load growth.
Which is unprecedented. I mean,
Yeah.
for the last 20 years, U.S. power demand has been virtually flat.
Yeah, like 0.5% of growth, maybe.
Right around there. Now, we are projecting growth rates we haven't seen since the economic boom of the 1950s.
And here is where the collision happens with our current energy transition goals. Because the natural instinct is to say, well, great, build more wind and solar farms to power the AI.
Right, but that narrative hits a hard thermodynamic wall pretty fast.
Because AI training runs are not like boiling a pot of water where you can just turn the heat down for a minute if the power dips. When you are training a massive language model, it's a synchronized, continuous mathematical process across tens of thousands of chips that can take months.
It's like a highly complex symphony.
Yeah.
If the string section randomly takes a 5-minute break because a cloud passed over a solar panel or, the wind died down in West Texas, the entire symphony collapses.
It's ruined.
Completely.
Yeah.
In AI terms, if you experience a voltage sag or a momentary power interruption, the computation desynchronizes. You don't just pick up where you left off.
You might have corrupted weeks of a multi-million-dollar training run.
Exactly. And you have to revert to an older checkpoint. So you need what the industry calls firm power.
Firm power, meaning high density, uninterrupted, 24/7, 365 electricity.
Yes. Which is why variable renewables, while entirely crucial for decarbonizing the broader residential grid, they simply cannot independently support a 500-megawatt AI campus.
Because the battery storage required to back up a campus of that size for even 3 cloudy days is economically and physically absurd. It would take up more land than the data center itself.
Precisely. And this uncompromising need for continuous baseload power is why the hyperscalers, the Amazons, the Microsofts, the Googles, are pivoting so aggressively toward nuclear energy.
Right, because nuclear power plants maintain the highest capacity factors of any energy source on Earth. They operate at full power more than 93% of the time.
Regardless of weather, time of day, or season, it just runs.
And if you look at the corporate moves, detailed in the legal briefs, it is a gold rush for electrons. It's happening right now.
Oh, absolutely.
Microsoft didn't just sign a power deal. They signed a 20-year agreement to literally resurrect 3 Mile Island Unit 1. Amazon secured access to nearly 2 gigawatts of existing nuclear power from Talon Energy in Pennsylvania.
And they've invested directly in X-Energy, right, targeting 5 gigawatts of new nuclear by 2039.
Yes. And Google is collaborating with Kairos Power to bring multiple reactors online. Meta is issuing massive requests for proposals specifically targeting nuclear generation.
This is a massive strategic realignment. For these companies, energy security has literally become tech security.
Wow, yeah.
If you fall behind in securing firm, clean power, you cannot build the data center. If you can't build the data center, you can't train the next generation model.
And if you can't train the model, you lose the AI race. It is an existential bottleneck.
Exactly.
But wait, here is where the math doesn't make sense to me. We are essentially trying to plug a supercomputer into a wall socket designed for a toaster. And traditional nuclear power plants, those massive gigawatt-scale concrete domes, they take decades to permit and build.
Decades, yeah. And they cost tens of billions of dollars.
Right. So if AI needs this firm power right now, or at least within the next 3 to 5 years, how does this possibly work?
Well, it doesn't.
Oh.
And that is the exact realization the tech and energy sectors have come to. The solution isn't building bigger power plants. The traditional model of bespoke gigawatt-scale construction is dead for this specific application.
So what's the alternative?
The solution is shrinking the reactors, standardizing their components, and building them in factories.
Which brings us to the concept of the SMR, the small modular reactor. When you read the engineering specs in these sources, it is a complete paradigm shift.
It really is. Let's break down the definition. Small generally refers to an electrical generating capacity of less than 300 megawatts per unit.
Okay.
But the revolutionary part of the acronym is modular.
Right, because traditional nuclear plants are essentially custom cathedrals. Every single one is a unique, bespoke mega construction project built entirely on site. You're pouring millions of tons of concrete in the rain. You're welding critical components in a muddy field.
And you are vulnerable to every weather delay, supply chain bottleneck, and local labor shortage imaginable.
Exactly. SMRs leverage the exact opposite philosophy. They leverage serial production. The primary systems, like the reactor vessel, the steam generators, they are designed to be fabricated within a controlled, sterile factory environment.
Think about how Boeing or Airbus manufactures airplanes, right?
That's a great analogy. They don't build the airplane on the runway. They build it on an assembly line, QA test it, and roll it out.
So once the module is built in the factory, you put it on a heavy haul truck or a specialized rail car, ship it directly to the data center site, and essentially plug it in.
Yep. And because it's modular, you don't have to build a 3-gigawatt plant all at once. An AI company can deploy a single 50-megawatt module to power their initial server racks.
Then 2 years later, when they expand the campus, they just order 3 more modules and daisy chain them together. It completely changes the capital risk profile. It shifts the risk from on-site construction variables to factory manufacturing efficiency.
And what is equally critical is the technological diversity within the SMR space. I found this part of the research fascinating. There are over 100 SMR designs in various stages of development globally.
And they largely fall into two camps.
Right. The first camp uses traditional light water reactor, or LWR, technology, designs like the NuScale Power Module or GE Hitachi's BWRX-300.
Yeah, these use the exact same basic physics and coolant light water as the large commercial reactors operating today, just engineered into a smaller integrated package.
And because the Nuclear Regulatory Commission is extremely familiar with water-cooled technology, these are generally considered the nearest-term solutions for deployment, right?
Generally, yes. But then you have the second camp, the Generation 5E designs. And this is where the science gets wild.
Oh, man, yeah. We are talking about reactors that don't use water as a coolant at all. They use liquid metals like sodium or lead or molten fluoride salts or high-temperature gases.
Let's look closely at the X-Energy X100. That's the specific reactor design that Amazon is aggressively backing. It is a high-temperature gas-cooled reactor, or HTGR.
Okay, so instead of using water to transfer the heat away from the nuclear core, it uses pressurized helium gas.
Right. Helium is noble, it doesn't become radioactive, and it doesn't corrode the internal components. But the true leap forward isn't the coolant, it's the fuel itself.
Trisofuel. I was reading the Department of Energy's analysis of this, and they literally call it the most robust nuclear fuel on Earth. How does it actually work?
TRISO stands for Tri-Structural Isotropic Particle Fuel. To visualize this, I want you to imagine a tiny kernel of uranium oxycarbide, about the size of a poppy seed.
Okay, super small.
Very small. That incredibly small seed is then encapsulated in multiple microscopic layers of specialized materials.
It's constantly compared to a jawbreaker in the literature.
A nearly indestructible microscopic jawbreaker. The core is surrounded by a porous carbon buffer layer, which absorbs the radioactive fission gases as they are produced. Then, it's wrapped in a layer of dense pyrolytic carbon, followed by a critical layer of silicon carbide, and finally an outer shell of more pyrolytic carbon.
Let's focus on that silicon carbide layer because that seems to be the magic ingredient here.
Sure.
In a traditional light water reactor, the uranium fuel pellets are stacked inside long metal tubes made of a zirconium alloy.
Right?
And the problem with zirconium is that if the reactor loses its water coolant and gets too hot, the zirconium reacts with steam, creates hydrogen gas, and eventually melts. That is what causes a meltdown.
Exactly. Zirconium has thermal limits. Silicon carbide, however, is a ceramic material that is so strong and so heat-resistant that it can withstand temperatures far exceeding the maximum possible temperature the reactor core could ever reach.
Wait, even in a worst-case accident scenario.
Even then,
So the fuel literally cannot physically melt down.
it cannot. In traditional nuclear power, we build massive billion-dollar reinforced concrete containment domes over the entire reactor to keep radioactive material inside in case of a breach.
Right, those iconic domes.
Yeah. But with TRISO fuel, the containment dome is essentially built into the fuel itself at the microscopic level. Every single poppy seed-sized particle acts as its own impenetrable containment vessel.
Which fundamentally changes where you can put these things. I mean, if the fuel can't melt and you don't need a 10-mile emergency planning zone, you can safely site these reactors right next to an urban center.
Or directly adjacent to an AI data center campus.
Exactly. And this leads us perfectly into the concept of passive safety. Because it's one thing to have tough fuel, but what happens to the reactor itself if the power goes out?
This is crucial.
The source material details an incredible piece of historical proof that I'd never heard of before, a reactor called EBR-2.
Oh, the Experimental Breeder Reactor 2,
Yep.
located out in the high desert of Idaho. If you want to understand why advanced SMRs are so fundamentally different from legacy nuclear power, you have to look at EBR-2.
What happened there?
Well, in the 1980s, engineers at the Argonne National Laboratory wanted to definitively prove the inherent safety of liquid metal-cooled fast reactors.
So they didn't just run computer simulations, they actually put the physical reactor to the test.
They did. The most famous of these tests was the SHRT-45R test, conducted on April 3rd, 1986.
Okay.
To understand the stakes, you have to realize that in a traditional commercial reactor, losing the flow of your coolant while operating at full power is the ultimate nightmare scenario.
Right, because if you lose coolant flow and the control rods fail to drop into the core to stop the nuclear chain reaction, the heat builds up exponentially in seconds. The metal claddings melt, the fuel turns to lava.
Exactly. But EBR-2 was a pool-type reactor cooled by liquid sodium, not water. So on that day in April, the engineers brought the reactor up to 100% full power.
Okay, full power.
Then they intentionally disabled the primary plant protection systems. the automated alarms and the emergency shutdown mechanisms.
Just reading the log of this made my heart race. They purposefully blinded the safety systems.
And then they manually turned off the primary coolant pumps. They deliberately initiated a total unprotected loss of flow accident.
That's insane. So the coolant stops moving, and the nuclear core is still generating massive amounts of heat. What happens next?
The temperature inside the core immediately began to rise, but because of the specific physics of the liquid sodium coolant and the metallic fuel, nature took over.
Nature.
Yeah. As the metal components of the core, the fuel pins, the grid plates began to heat up, they physically expanded.
Oh, thermal expansion, like how a bridge has expansion joints because metal swells in the summer heat.
Precisely. But at the atomic level inside a nuclear reactor, geometry is destiny. When the metal core expanded radially, it physically pushed the uranium fuel atoms slightly further apart from each other.
Okay.
In nuclear physics, for a chain reaction to sustain itself, a neutron from one split atom must hit another atom. If the atoms spread out, the neutrons have a higher probability of leaking out of the core without hitting anything. The mean free path changes.
So simply by expanding, the rate of the fission chain reaction naturally slowed down.
The laws of physics literally stepped in and hit the brakes. The reactor shut itself down.
Without a single human operator touching a dial.
And without a single automated computer system firing. Within moments, the reactor safely shut itself down purely through inherent thermal feedback.
Wow.
The reactor inlet and outlet temperatures naturally reached a safe, convective equilibrium. There was zero fuel damage. In fact, they started the reactor right back up to full power a few hours later.
What's fascinating here is how this shifts our entire philosophy of risk. Safety is no longer about active human intervention. It's no longer about requiring massive backup diesel generators to kick on to run emergency water pumps.
Exactly. Safety is baked into the undeniable, immutable laws of physics. Advanced SMRs are building entirely on this legacy. They are designed to be walk-away safe.
Okay, so let's pause and synthesize where we are. We have solved the hardware problem. We have TRISO fuel that is basically indestructible. We have reactors that physically expand and shut down if the cooling fails. We've bottled the energy of the sun in a factory-built walk-away safe shipping container.
Basically, yeah.
But if you take a step back, this creates a massive orchestration nightmare. Think about it. We are talking about replacing centralized gigawatt plants, where you have a massive control room staffed by 800 highly trained humans, with dozens, maybe hundreds of these small autonomous nuclear reactors scattered around a metropolitan area.
Directly powering individual AI data centers.
Right. Who is driving the bus? If the grid is decentralized, how do all these individual reactors talk to each other to balance the load?
That is the perfect pivot to the digital side of the equation. Because a physical reactor is only half the story.
And this is where we found a coincidence in the research that I absolutely loved. In the nuclear engineering world, SMR stands for Small Modular Reactor. But when you switch over to the computer science papers detailing how to control a decentralized grid, SMR stands for something else entirely.
It stands for state machine replication.
I mean, you can't write a better metaphor for convergence than an acronym collision like that. I looked at this computer science concept, state machine replication, and honestly, I was completely lost for a minute. From what I gather, it's basically a paranoia protocol, right?
The paranoia protocol, that's a fun way to put it.
It assumes every device on the grid might be broken or delayed or receiving bad data, so it forces them all to mathematically agree on reality.
That's a very good way to frame it. To understand state machine replication, you have to understand the fundamental challenge of a decentralized network, which computer scientists often refer to as the Byzantine generals problem.
Explain that for the listener, because it's crucial here.
Okay, imagine several generals of the Byzantine army encamped around an enemy city. They can only communicate by sending messengers. They must agree on a coordinated plan of action, either all attack at once or all retreat.
Because if only some attack, they will be slaughtered.
Right. But some of the generals might be traitors who will intentionally send false messages to confuse the loyalists. Furthermore, some messengers might be intercepted or delayed. How do the loyal generals reach a consensus and execute the same plan despite the chaos and betrayal?
Map that onto our power grid.
The generals are the independent nodes on the grid. A solar inverter, a battery controller, an AI data center load manager, and a physical nuclear SMR.
Right.
They are not traitors, obviously, but they are subject to latency, hardware degradation, and sensor failure. If one node thinks the grid voltage is plummeting and another node thinks the grid voltage is spiking, they will take conflicting actions.
One injects power, the other pulls power, and you get a cascading blackout.
Exactly. So how do you ensure they all agree on the current reality of the grid without a centralized boss telling them what to do?
That is what state-machine replication solves. It is a foundational consensus protocol. It ensures that a cluster of distributed computers remains perfectly synchronized.
Yes, it works by treating every single node on the network as a deterministic state machine.
Deterministic meaning, if I give you X input, you will always, 100% of the time, produce Y output.
Exactly. For the cluster to remain synchronized, the protocol ensures that every single node receives the exact same sequence of inputs in the exact same chronological order.
Okay, so if they all start from the same initial state, and they all process the identical sequence of events, they will all arrive at the identical new state.
You've got it. So if a cloud covers a solar farm and voltage drops across the network, the state machine replication protocol ensures that every single nuclear reactor, every battery, and every data center processes that voltage drop data simultaneously and agrees on the new state of the network.
And this leads to the concept of cluster reasoning. To manage this 21st century grid, you pair the physical SMRs, the small modular reactors, with the computational SMRs, the state machine replication protocols. They become a single, self-governing entity.
And this reasoning, this consensus, has to happen incredibly fast. If you detect a frequency anomaly on the grid, you cannot rely on sending that data packet back to a centralized cloud server in Virginia, having an algorithm process it, and sending a command back.
Because the latency, the round-trip travel time of the data is too high,
Yeah.
by the time the command arrives, the grid has already destabilized.
Exactly. So you have to process the data locally. You have to use edge AI.
Meaning you embed artificial intelligence directly into the devices at the edge of the network, right at the substation controller, right at the smart meter, right at the reactor's output valve.
Right. And to do this without latency, the hardware itself is changing. The research points heavily to the use of field programmable gate arrays, or FPGAs.
Now, I want to clarify this for the listener because the distinction between a normal computer chip and an FPGA is fascinating. A normal CPU processes instructions sequentially, right? Fetch the data, decode the instruction, execute the math, store the result. It's incredibly fast, but it's fundamentally doing one thing at a time in a loop.
Correct. But FPGA is literally a blank canvas of hardware logic blocks. Instead of running software on a fixed chip, you physically rewire the microscopic logic gates on the chip to match the specific algorithm you want to run.
And you physically rewire it.
We'll digitally rewire the physical pathways, yes. So if you want an AI to constantly monitor grid voltage, you literally wire the silicon to be a dedicated voltage monitoring circuit, which means it processes data in parallel, instantly, without the overhead of an operating system.
That's wild.
Yeah.
And because the logic is baked into the physical circuitry, an FPGA at the edge of the grid can achieve AI inference times of under 20 microseconds.
Under 20 microseconds, it's almost instantaneous.
20 microseconds, that is incomprehensibly fast. But, and I have to push back here, I really do, we are talking about the power grid. It is the single most critical, dangerous piece of physical infrastructure we have.
It is.
If you were telling me that the grid is making its own decisions, without a human in a centralized control room acting as a sanity check in fractions of a millisecond, well, that doesn't just sound like a technological marvel. That sounds like a recipe for absolute chaos.
I completely understand why you'd say that.
Like, what happens when an AI agent gets a bad sensor reading and makes a mistake at 20 microseconds? It feels like we're building a house of cards.
It is an entirely valid concern, and it is the primary reason why traditional utility operators are deeply skeptical of decentralization. But the advanced research we are looking at argues that it is not chaos. It is actually a highly structured, remarkably resilient form of biomimicry.
Biomimicry.
Yes, we are moving away from a brittle, mechanical paradigm and toward an organic one. The grid is learning to operate like a human brain.
And that brings us to the most visionary part of the source material, the concept of the radial brain, or distributed neural architecture.
Right. If you look at the legacy power grid, it is a rigid top-down hierarchy. You have massive generation at the top, high-voltage transmission lines in the middle, and passive consumers at the bottom.
Because it is hierarchical, it is brittle.
Exactly. If a major transmission substation goes down, or a central gigawatt plant trips offline, the shockwave cascades through the system. You get regional blackouts. It has massive single points of failure.
But biological nervous systems don't work like that.
No, they don't. If you suffer a minor injury and damage a small cluster of neurons, your brain doesn't shut down. It inherently reroutes the signals around the damage. It is self-healing, adaptable, and highly resilient.
So if we map this biological analogy onto our new power grid, the physical nuclear SMRs, the data centers, the massive battery banks, they act as the neural somas, the cell bodies. They are the primary generation and processing units.
Perfect.
And the edge AI controllers, the smart inverters, the FPGAs, they act as the synaptic junctions connecting the cells.
That is exactly the mapping the researchers use. And just like in a biological brain, the connections between these grid nodes, the synapses, are not static, they are dynamic. They learn and adapt through a process called spike timing dependent plasticity, or STDP.
Now, STDP is a term I've only ever heard used in neuroscience to explain how humans form memories or learn new physical skills. It's the mechanism behind the old phrase, neurons that fire together wire together.
Right.
How on earth does human memory formation apply to a network of nuclear power plants?
It is a brilliant application of neuromorphic engineering. In a neural grid, STDP means the grid literally learns from its own operational experience over time.
Okay, let's walk through a concrete scenario for the listener. Put us in a neighborhood. Imagine a massive, sudden cloud bank rolls over a 100-megawatt solar farm on the edge of a city. The power output trains instantly. The voltage on the local grid starts to sag. What happens in an STDP-enabled SMR cluster?
Okay, so in a fraction of a millisecond, the distributed sensors detect the voltage sag. The various autonomous agents managing the local SMRs evaluate the state of the grid using their edge AI.
Right.
Let's say reactor node A senses the instability and autonomously decides to inject a burst of reactive power into the grid right before the frequency drops below critical limits. It perfectly stabilizes the local network.
Awesome. Then what?
The computational protocol, the state machine replication, analyzes the timeline. It sees that node A fired, and immediately after, the grid stabilized. Because the action was successful, the STDP algorithm mathematically increases the synaptic weight of node A.
Meaning the system trusts node A more now.
Precisely. The network organically learns that node A is a highly reliable contributor to stability in that specific topological area.
And what if a node messes up?
Well, conversely, let's say node B reacts slightly too late, and its power injection accidentally exacerbates the instability, causing a momentary voltage spike. The system sees the negative outcome, and the synaptic weight of node B is depressed. Its influence on future consensus decisions is reduced.
That is mind-blowing.
Right.
Millions of these microtransactions, these little successes and failures, are occurring every hour. The grid is essentially building its own muscle memory.
It is.
It is organically evolving an optimal routing architecture without a human engineer ever writing a specific line of code dictating, if this happens, do that.
Yeah.
It learns to balance itself.
Yes. And to facilitate this constant high-speed negotiation, the system utilizes what are called multi-agent systems, or MAS. Instead of one master algorithm trying to compute the physics of an entire city, you have specialized autonomous agents handling distinct functional domains: perception, cognition, action, coordination, and explanation.
Let's dig into the coordination agents, because that's where the security risk comes in. You might have a voltage control agent operating inside a hyperscaler's AI data center, and it needs to negotiate for power with a flexibility aggregator agent operating in an SMR cluster 3 miles away.
Right, they're negotiating peer-to-peer.
But obviously, for national security reasons, you cannot have external software agents peering into the internal physics data of a nuclear reactor. So how do they collaborate without exposing sensitive data?
They utilize two advanced cryptographic techniques: federated learning and homomorphic encryption.
Okay, explain federated learning first.
Federated learning allows the agents to train a shared machine learning model without ever exchanging raw data. The data center agent and the nuclear plant agent both download a baseline AI model. They train it locally on their own highly classified private data.
So the data stays put.
Yes. Then they only share the updates to the model, the mathematical gradients, with the network. The network gets smarter as a whole, but the raw data never leaves the local facility.
And to protect those model updates while they are in transit, they use homomorphic encryption. I want to explain this clearly because it is essentially cryptographic magic.
It really is.
Normally, if you want a cloud server to perform a calculation on encrypted data, the server has to decrypt the data, do the math, and then re-encrypt it. During that decryption window, The data is vulnerable to hackers.
Exactly. But homomorphic encryption allows you to perform mathematical operations on the ciphertext while it is still encrypted.
The source used a great way to visualize it, the locked box analogy.
Oh, yeah, the baker analogy.
Right. Imagine you have a highly sensitive recipe and you need a master baker to optimize the ingredient ratios, but you cannot let the baker see the actual recipe.
Right, it's a secret.
Homomorphic encryption is like putting that recipe inside an impenetrable lockbox that has specialized gloves integrated into the sides. The baker puts their hands into the gloves, blindly manipulates the ingredients inside, and optimizes the mixture perfectly. They then hand you back the lockbox.
The baker never saw the raw ingredients, but they successfully performed the complex operation.
That perfectly illustrates it. The agents can optimize the power flow of the entire city while maintaining an absolute, impenetrable cryptographic wall around the nuclear assets.
It's elegant.
It is. If we connect this to the bigger picture, what we are talking about is replacing a fragile, dumb machine, the 20th century grid, with a highly secure, self-healing organism, an organism that can autonomously detect an anomaly, isolate a failing transformer, and reroute power from an SMR cluster seamlessly, all in the 20 microseconds it takes an FPGA to process the data.
It is a stunning vision of resilient infrastructure.
It is a beautiful theory. It really is. But, and this is a massive buddy, this biomimetic organism does not exist in a vacuum. It exists in the real world.
And the real world is complicated.
Very. Putting it into practice requires billions of dollars in capital, it requires navigating archaic regulatory bureaucracies, and it has massive disruptive implications for human jobs and energy economics.
We have to step back from the elegant theoretical physics and look at the harsh, unforgiving realities of the market.
And this is where the sources force us to look closely at the economics and the deeply skeptical counterargument.
We must. The traditional nuclear industry relied entirely on a financial concept known as the economy of scale.
Right. Bigger is cheaper.
Brutally simple logic. Building the containment structures, navigating the licensing, and staffing the security for a nuclear plant has massive fixed costs. So, to make the electricity affordable, you build the reactor as massive as physically possible, 1,000, 2,000 megawatts, to spread those fixed costs over millions of megawatt hours.
But SMRs flip that paradigm on its head.
Yeah.
By definition, they are small. They intentionally abandon the economy of scale.
Exactly. So, to survive economically and produce electricity at a competitive price, the sources argue they must pivot to the economy of automation.
Meaning they have to drastically lower their operational and maintenance costs. You cannot economically justify staffing a 50-megawatt SMR with the same 800-person security and engineering workforce required to run a massive gigawatt-scale plant.
The levelized cost of energy, the LCOE, would completely collapse. They are financially mandated to use the edge AI and the neural grid logic we just discussed to run the plant with an absolute minimum of human staff.
Even if you assume the automation works perfectly, the upfront capital costs are currently a massive hurdle. Let's look at the numbers from the University of Illinois Urbana-Champaign campus microgrid study included in our research.
Those numbers were eye-opening.
Yeah. They modeled replacing their traditional fossil fuel burning natural gas plant with a modern 42-megawatt advanced SMR. The environmental win was undeniable. The model showed an 85% reduction in carbon dioxide emissions.
A huge win for the climate.
But the financial cost of that decarbonization? The model showed a 587% increase in installation costs compared to simply building another gas plant.
587%. That is a sobering, brutal number for any utility executive to look at. And it brings us to a critical perspective we must include to maintain a balanced view.
Yes, let's talk about the World Nuclear Industry Status Report, or WNISR.
Right. This is an annual, highly rigorous, independent assessment of the global nuclear sector, and it takes a deeply skeptical, almost scathing view of the current SMR landscape.
Following our strict rule of impartiality, it's vital we convey their arguments in detail.
The report uses a very evocative historical term to describe the SMR industry today: a Potemkin village.
A Potemkin village. For those unfamiliar, that refers to an impressive, elaborate facade designed solely to hide an undesirable or failing reality from onlookers.
Precisely. The authors of the WNISR argue that despite the glossy architectural renderings, the breathless press releases, and the headlines about tech giant partnerships, the actual reality on the ground does not match the hype.
First and foremost, they point out a fundamental, irreconcilable mismatch in timelines. As we discussed earlier, AI data center demand is surging in immediate cycles of 3 to 5 years. The hyperscalers need power now.
But nuclear development, even for modular SMRs, is still beholden to nuclear timelines. It takes a decade or more.
Right. You have to secure the site, conduct years of seismic and environmental reviews, navigate the Nuclear Regulatory Commission's licensing process, establish a completely new, untested supply chain for components like TRISO fuel, and then actually construct the facility.
The report explicitly states that relying on new nuclear plants to solve the immediate AI energy crisis is incoherent.
Wow, they use the word incoherent.
Yes. They argued that a competing array of solar power plants and battery storage can be manufactured, permitted, and connected to the grid in a matter of months, while an SMR project will be mired in paperwork for years.
Furthermore, the skeptics point away from the theoretical models and point directly to recent, high-profile financial failures in the real world.
The most prominent example is Nuscale.
Yeah, let's talk about Nuscale. Nuscale was the golden child of the American SMR movement. They were the very first SMR design to receive official design certification from the U.S. Nuclear Regulatory Commission.
They had a flagship project planned in Utah, the Carbon-Free Power Project, backed by a coalition of municipal power systems.
But the project completely imploded.
It did. The projected costs spiraled out of control due to inflation, rising interest rates, and the soaring cost of raw materials like steel and specialized concrete.
The target power price jumped from around $50 per megawatt hour to nearly $90. At that price, it was no longer economically competitive with natural gas or renewables, and the municipal subscribers started pulling out.
Nuscale was forced to completely cancel their flagship project before a single shovel hit the dirt.
The critics look at that and say, see, modularity doesn't solve the fundamental financial risks of nuclear power.
The WNISR also notes that while Amazon, Google, and Microsoft are making massive headlines with their investments, if you actually look at the ledger, the dollar amounts being committed right now are essentially seed money.
They are a drop in the bucket compared to the tens of billions of dollars required to actually build out a widespread commercial fleet of hundreds of SMRs. The skeptics argue the risk is still largely resting on the shoulders of the developers and, potentially, the taxpayers through government subsidies.
Exactly.
So what does this all mean? As an observer watching these two worlds collide, what do we make of this? Is this biomimetic, autonomously orchestrated neural grid an inevitable technological revolution? Or is it a hyper-expensive, decades-away pipe dream being sold to desperate tech companies who realize they are running out of electricity?
It is the central defining tension of the modern energy transition. The optimists, the engineers building these systems, believe deeply in the learning curve.
Right. They believe that once we get past the painful, expensive, first-of-a-kind costs of building the initial prototypes and we successfully transition to nth-of-a-kind serial factory production, the costs will plummet.
They point to the exact same cost curves that made solar panels and lithium-ion batteries dominant.
But the skeptics, armed with decades of historical data, believe the nuclear industry's track record of massive cost overruns, supply chain failures, and delays will inevitably repeat itself, regardless of whether the reactor is big or small.
But here is the undeniable truth that we found in the sources. Regardless of whether widespread deployment takes 5 years or 15 years, the foundational architecture of the grid, and crucially, the legal and regulatory framework that governs it, is already being aggressively rewritten.
The rules of the game are changing to accommodate a world where machines, not humans, do the heavy lifting. Which brings us to our final core topic, the human element and strategic autonomy.
This is where it gets really interesting.
Because if the machines are autonomously running the physical grid and the edge AI is making millisecond decisions, what exactly happens to us? What is the role of the human operator in the 21st century?
Let's start by looking at why the hyperscalers are driving this change so aggressively. Why are Amazon and Microsoft so obsessed with getting their own dedicated behind-the-meter nuclear reactors?
It is not just about having clean, zero-carbon energy for their ESG reports, is it?
No, it's about a strategic concept called island mode.
Island mode, explain that.
Island mode is a critical, highly sought-after capability for an SMR cluster. It means that the local microgrid, for example, a massive 500-megawatt AI training campus, and its dedicated cluster of Gen IV high-temperature reactors can physically and digitally disconnect from the broader public power grid and operate completely independently.
They throw a massive switch, decouple the substations, and literally become an energy island.
Exactly. We are living in an era of increasing global instability. We have seen the fragmentation of supply chains, the rising frequency of extreme, grid-destroying weather events, and an escalating landscape of state-sponsored cyber threats to critical infrastructure.
Tech companies are looking at this landscape and demanding strategic autonomy. If the regional public grid collapses due to a severe winter freeze like we saw in Texas, or a targeted cyber attack takes down transmission lines, or capacity shortages force rolling blackouts across a state, the AI campus in island mode doesn't even blink.
Because its power source is physically disconnected from the chaos, it continues to run its massive model training runs, powered by its own private nuclear fuel reserve that, depending on the reactor design, can last for years or even a decade without needing to be refueled.
It is the ultimate insurance policy for the digital age. It guarantees the continuity of the most advanced computing infrastructure on Earth, regardless of what happens to the society around it.
But operating a massive fleet of private, automated nuclear reactors requires a complete rethinking of how we license and regulate human operators. You can't use 1970s regulations for 2020s technology.
And this is where the Oklo regulatory filing to the Nuclear Regulatory Commission is so incredibly revealing. It is a glimpse into the legal future.
It really is. Currently, if you want to be a licensed nuclear reactor operator in the United States, you go through years of grueling training, and you are licensed to a specific, unique physical facility.
If you work at the Voldel plant in Georgia, you can't just walk into the Dresden plant in Illinois, sit down at the console, and take control. The dials, the physics, the piping, they are entirely different.
But Oklo, an advanced fission company developing a fast microreactor called the Aurora Powerhouse, is formally proposing something radically different to the regulators: product-based operator licensing.
They argue that because their SMR modules will be standardized, identically manufactured factory-built products, a human operator should not be licensed to a single geographic location. They should be licensed to the product line itself.
The analogy they use in the filing is brilliant. It's exactly how the Federal Aviation Administration licenses commercial airline pilots. A pilot spends hundreds of hours in a simulator and gets a type rating to fly a Boeing 737.
Right. Once they have that license, it does not matter if that specific 737 is sitting on a tarmac in New York or London or Tokyo. The cockpit is identical, the physics are identical, the pilot is licensed to operate the machine, regardless of its location.
Oklo is pushing to license nuclear operators the exact same way. You don't get a license for the reactor in Ohio, you get a license for the Aurora Powerhouse version 1.0, and you can operate any of them globally.
But here's the critical pivot. This entire legal framework of product-based licensing is utterly dependent on the technological breakthroughs we discussed in the first half of this deep dive, the passive safety and the deep automation.
In the Oklo filing, they detail what they call Condition 1, the foundational prerequisite for this new regulatory framework to be approved by the government. The condition states explicitly, safety functions are achieved without reliance on human actions.
That is a staggering sentence to read in a federal nuclear regulatory document, without reliance on human actions.
It represents a paradigm shift in nuclear safety philosophy. In the current operating commercial fleet, human operators are actively credited in the probabilistic risk assessments and safety analyses.
If a pump fails or a valve sticks, a highly trained human being must diagnose the problem, manually flip a switch, or hit the big red button to initiate a scram and shut down the reactor to protect the public. The human is the ultimate safety net.
In the Oklo model and in Gen IV SMRs broadly, because of the inherent physics of the thermal expansion we talked about with EBR2 and the indestructible Trizo fuel and the 20 microsecond response time of the Edge AI, human beings are explicitly not needed to uphold safety.
The machine protects itself. It is mathematically incapable of melting down and computationally capable of balancing its own load. So if human operators are no longer sitting in a control room staring at dials, ready to save the day in a high-stress emergency, what exactly is their role? Why employ them at all?
The role of the human shifts fundamentally from active controller to system overseer. Oklo's filing outlines the creation of a centralized powerhouse support center.
Instead of having an 800-person staff and a dedicated control room built at every single individual reactor site across the country, you have one secure remote centralized hub staffed 24/7 by a much smaller team of highly specialized personnel.
These operators are known as startup operators. They monitor the telemetry of the entire fleet of dispersed SMRs on giant screens. They manage the complex initial startup processes when a new module is brought online.
They analyze the long-term predictive maintenance data generated by the AI digital twins of the reactors to foresee component wear and tear. And they provide deep off-shift engineering expertise if the autonomous systems detect an anomaly they cannot classify.
Right. It's a completely different job description.
So let's look at the complete picture we've drawn today. We have field programmable gate arrays and state machine replication protocols acting as the synaptic junctions, handling the millisecond to millisecond of voltage and frequency balancing at the edge of the grid.
We have the immutable physical laws of liquid metal thermal expansion and silicon carbide fuel acting as the infallible safety brakes, physically preventing catastrophic meltdowns.
And sitting above all of it, we have a small team of humans sitting in a centralized hub miles away,
Yeah.
acting as fleet managers rather than drivers, watching the organism balance itself.
That is the ultimate orchestration of the next intelligence phase. It is the total fusion of advanced, inherently safe physical nuclear infrastructure and decentralized biomimetic artificial intelligence.
Which brings us to the end of our deep dive today. Let's pull all of these massive concepts together for you. We started by looking at a collision. The limitless digital ambition and exponential compute scaling of artificial intelligence crashing headfirst into the fragile, physical limitations of an outdated, mid-20th century power grid.
And to solve this bottleneck, to prevent the AI revolution from starving for electrons, we are watching the birth of an entirely new infrastructural paradigm, SMR clusters.
We are completely abandoning the concept of building bespoke gigawatt-scale power plants. Instead, we are shrinking nuclear reactors, manufacturing them sequentially on factory assembly lines, and designing them using generative physics to be inherently walk-away safe.
We are then taking dozens of those physical modular reactors, scattering them across industrial sites, and networking them together using state machine replication and biomimetic neural grid logic.
We are effectively replacing a rigid top-down hierarchy with a self-healing radial brain that uses spike timing-dependent plasticity to literally learn from its own operations and organically route power where it is needed, instantly.
And while there is intense, mathematically valid skepticism from watchdogs about the near-term economic viability, the staggering upfront capital cost, and the painfully slow historical timelines of nuclear construction, the reality is that the regulatory groundwork and the technological hardware are already being aggressively deployed. The tech giants are forcing the issue through sheer financial will.
The internet you scroll, the generative AI you use to write your emails, and the physical power grid running the lights in your city are no longer separate, distinct entities. They are merging into a single, integrated, decentralized organism. You should care deeply about this transition because the success or failure of this convergence will dictate the cost of your electricity, the reliability of your infrastructure, and the environmental impact of our entire digital future.
This raises an important question, regarding our relationship with the infrastructure we rely on every day. We are rapidly moving from a 20th century world where we directly command our machines to a transitional world where we collaborate with them, to a near future world where increasingly we merely supervise them as they govern themselves.
And that leads me to a final thought, a provocation I want to leave you with, something to mull over as you go about the rest of your day, look at your phone, or type your next prompt into an AI. Throughout this entire deep dive, we've talked in great detail about building an autonomous, self-healing grid that uses embedded artificial intelligence and biomimetic neural logic to route immense amounts of power.
Right.
And the explicit primary purpose of this new, brilliant grid is to feed the massive data centers that are busy training and creating even more capable artificial intelligence. So I have to ask, are we simply building the infrastructure for a smarter, cleaner power grid to keep the lights on? Or are we, entirely by accident, busy building the global AI its own physical nervous system? Thanks for joining us on this deep dive. Stay curious.